9.8 Lesson 2 Power Series. We have two objectives for today. Objective 1, given a power series where the domain of this power series is the set of all x for which the power series converges. So when we talk about the domain of a power series, we're talking about the values of x for which the power series converges. So to our vocabulary, we can add domain of a power series. So by the domain of a power series, we mean the values of x for which the power series converges. So given a power series where the domain of the power series is the set of all x for which the power series converges, you will be able to find the derivative of the power series by differentiating the power series that's given, and you'll be able to find the integral of the power series by integrating the power series that is given. And objective 2 is this. We're going to look at a theorem, 9.21, properties of functions defined by power series, and when you use that theorem, it will reduce the work needed to find the intervals of convergence for the power series for the original power series, the derivative of it, and the integral of it. So you don't have to do everything over again. This theorem will help you to find the intervals of convergence for the original power series, its derivative, and its integral without having to do so much work. So our vocabulary is power series centered at C, radius of convergence, endpoint convergence, interval of convergence, and we're adding to that the domain of a power series. So here we have theorem 9.21, properties of functions defined by power series, and let's take a look at this. So we have a function given by this power series, and if you write out the terms of the power series, you begin with n is equal to 0. So substitute 0 where you see n, and you will have a naught, a sub 0, times x minus c to the 0 power, which we agree is equal to 1. And then you have a sub 1 times x minus c to the first power. You have a sub 2 times x minus c to the second power, a sub 3 times x minus c to the third power, and so on. So that's pretty straightforward. What we have is a power series centered at C. So we have a function given by this power series, and let's say it has a radius of convergence r that's greater than 0, maybe 1, maybe 5, maybe 7, maybe 1/2, whatever that radius of convergence may be. Then on the interval, so basically you start at the center of the power series and you go r, which is the radius of convergence, to the left of the center, and you go r to the right of the center. So for example, let me draw a number line here. So let's say this is the center of our power series at some value c. It could be 2, it could be -1, it could be 5, it could even be 0. And then, so you have the radius of convergence r. So you're going to go r units to the right of the center and r units to the left of the center. So here you have c minus r, and here you have c plus r. So that's what we're talking about. So let's read the theorem once again. So what you have is a power series centered at C, and we're given that it has a radius of convergence r greater than 0. Then on this interval that we just discussed, that this power series function f is differentiable, meaning you can take the derivative of it. And differentiability implies continuity, as you learned in the early part of Calculus AB. So differentiability implies continuity. So on this interval, the function f for the power series function f is differentiable and therefore continuous. Moreover, the derivative and antiderivative of f are as follows. So this theorem allows us to take a given power series and differentiate it to find f prime of x and integrate it to find the indefinite integral of f of x dx. So we'll take a look at that. But before we look at that, let's look at the last paragraph in the statement of the theorem. It states here that the radius of convergence of the series obtained by differentiating or integrating a power series is the same as the radius of convergence of the original power series. So you only have to do the ratio test one time. You only have to do the ratio test for the original power series, and that would tell you the radius of convergence for the original power series as well as the derivative and the integral of the original power series. However, the theorem states that the interval of convergence may differ for these three series as a result of the behavior at the endpoints. So basically, what this theorem allows you to do is apply the ratio test once for the original power series and get a radius of convergence, and these two power series must have the same radius of convergence. However, the behavior at the endpoints are not necessarily the same. So all you have to do is use the ratio test once to find the radius of convergence for all three power series, but then you have to check for convergence at the endpoints separately for each of your three power series for the original, the derivative, and the integral. And you could also find a power series for even like the second derivative. So I want to continue by having you look at what we're seeing here with Theorem 9.21. So how do you find the derivative of a power series? Well, look at these terms. These are just polynomial terms. So you use the power rule to find the derivative of a power function, because each of these terms are power functions of x. Each of these terms are power functions of x. And remember, we have a function of x, and we're finding the derivative of f with respect to x. Okay, so we're differentiating with respect to x, we're integrating with respect to x, so the variable that we are integrating with or differentiating with respect to is x. So not n, but x. That's important for you to understand. So now the n is just the index for the summation that you have, but the variable of integration with respect to and differentiation with respect to is x. So each of these terms in your power series are power functions, and you are going to differentiate each of these terms using the power rule for differentiation, and you're differentiating with respect to x. So take a look at that. So if you have a constant term, the derivative of a constant term is 0. How do you differentiate this term? It's a first degree power function, so you just get a sub 1 when you find the derivative of it. How do you differentiate this term? It's a second degree power function, so you would bring the exponent 2 to the front, and you would get 2 times a sub 2 times x minus c to the first power, because you subtract 1 from the exponent, and you keep on doing that for the remaining terms in your power series. So you would bring the 3 to the front, so you have 3 times a sub 3, subtract 1 from the exponent, and you will have x minus c to the second. Now that's what you're doing, term by term. But of course, you can just do that generally for using the formula given for the nth term. So what do? You take the exponent and you bring that to the front. So you will have n times a sub n, and the power rule for differentiation says subtract 1 from the exponent. And that's exactly what we're doing here. Now notice that you do have to be careful with the index, because you cannot have the exponent here be a negative number. The least that exponent can be is 0, so you want to make sure that you adjust the index as needed. If you need to adjust it so that the exponent here will not be negative. So we cannot have n start at 0 because that would make the exponent negative, and we don't have that when you differentiate each of these terms. So it wouldn't be right. So you need to make n start at 1 for that reason. So that's what we have. And if you are ever in doubt about what the index should start at, just write the first couple of terms of the original power series and differentiate those term by term, and just make sure that you get those two terms. Just make sure that you get the derivatives of those two terms in the power series for f prime. So what about integration? How do you do that? You also do that term by term. How do you integrate a power function? You use the power rule for integration. So look at each of these terms. Each of these terms are power functions of x. Now this is a constant term, but how do you integrate, for example, if you have f of x is equal to a sub 3 times x minus c to the third power? The integral of f of x with respect to x would be, you need to use the power rule for integration. You need to add 1 to the exponent and divide by the new exponent. So you will have a sub 3 times x minus c to the fourth power divided by 4 with a constant of integration. So that's essentially what we're doing here. And we're just doing that term by term. And you can see that we have a constant of integration that we write out front. So we write that first. So we have our constant of integration, c. And then you can see here that we're doing exactly what you saw me do right here. What are we doing? We're adding 1 to the exponent, so the n here becomes n plus 1, and we're dividing by the new exponent of n plus 1. Just like I did here with my example, I added 1 to the exponent of 3, got 4, and divided by my new exponent. So in general, what are we doing? We're adding 1 to the exponent of n to get n plus 1 and dividing by the new exponent of n plus 1. So that's the general description. That's the general description that we have for the terms of the power series for the integral of f of x with respect to x. And if you were to try to check that on a term-by-term basis, you would do something similar to what I'm erasing now, and you're just going to go ahead and do term-by-term integration for each of these terms, and you're going to get what we have here. But this is the general formula. So the index here starts at 0, and again, if you're ever in doubt about what the index should start at, just write the first couple of terms of the power series for f and integrate those two terms term by term. And whatever index you should have here can be determined by making sure that you get the antiderivatives of the first two terms of the power series for f. So you can, if you're ever in doubt, you can do that. But as a general rule of thumb, for the index for the derivative, you want to make sure that it is such so that this exponent is not negative. And here, you can generally keep it to be the same as whatever the index started with for the function f of x. So again, something that we said earlier is all three of these power series will have the same radius of convergence. So there is no need for you to do the ratio test 3 times. You only need to do it once. However, you do need to check for the convergence at the endpoints for each of these separately, because they could have different behavior at the endpoints. Example 8, we have this power series. from n is equal to 1 to infinity, and the nth term is x to the n over n. So we see that our power series is centered at c is equal to 0. And these are the first three terms of the power series. Just substituting n is equal to 1, 2, and 3 will give us these three terms. So what do we want to do with this problem? We want to find the intervals of convergence for the power series that's given, its derivative, and its integral. So using the theorem that we just learned about, we can easily find the power series for the derivative and the integral by looking at the given power series and integrating the nth term with respect to x, or differentiating the nth term with respect to x. So the power series for f of x is given, so I'll just write that here underneath b. And the power series for f prime, it's easy to find. All you have to do is write the summation notation, and okay, I'm going to sort of leave this blank for a while so that we can decide what to write there after we do the differentiation on a term-by-term basis. So you're differentiating with respect to x, so you treat n as a constant because you're differentiating with respect to x. So you're going to take that n and use the power rule, bring that to the front, and subtract 1 from the exponent. So when you do that, you're going to have n, and you'll have x to the n minus 1 over n. So now you can cancel the common factors of n, and you just get x to the n minus 1. So you have x to the n minus 1. So it is okay for n to start at 1 because that's not going to make the exponent negative. And again, if you're in doubt, just look at the first three terms of the power series for f of x, and you know that if you were to differentiate x with respect to x, you're going to get 1. And you know that if you were to differentiate x squared over 2 with respect to x, you're going to get x. And here you're going to get x squared. So as I have it here, will it give me these three terms? If you substitute 1 for n here, you get 1 minus 1 is 0, and x to the 0 is 1. If you substitute the next value of n, which is 2, 2 minus 1 is 1, so you get x to the first. If you substitute n is equal to 3, 3 minus 1 is 2. So it is correct. You can always check by doing exactly what you just saw me do. So now the next thing that you want to do is write the power series for the integral. And how will you do that? You need to begin with the constant of integration. Write c plus. And then you're going to write the summation notation. Again, I can start at n is equal to 1, but you can also leave it blank for now if you like, just to verify. And all you're doing is what? You're going to integrate with respect to x. You treat n as a constant. So you're integrating with respect to x. So you look at the n here, and you're going to do what? You're going to add 1 to the exponent and divide by the new exponent, because that is the power rule for integration that we learned in calculus AB. So we're going to have x to the n plus 1 divided by n times n plus 1. Divided by n times n plus 1. And in fact, that is correct. And you can start at n is equal to 1. Usually for the integration, it's the same as whatever you had here to begin with for the original function. And again, if you're ever in doubt, you can just verify by integrating the first couple of terms of the power series for f of x. If you integrate each of those terms, you should get x squared over 2 plus x cubed over 2 times 3, and so on. And you can just make sure that what you have here will give you these terms of the power series. So if you start at n is equal to 1, you will have 1 plus 1 is 2, yes. And then you have 1 times 1 plus 1. 1 times 2 is 2. If n is 2, you have 2 plus 1 is 3, yes. And then you have 2 times 2 plus 1, 2 times 3. That's correct. So what we've done is we've found the power series for the integral of f of x with respect to x. The power series for f of x was given, and we found the power series for f prime. The next thing that we have to do is we have to find the intervals of convergence for each of these. So we will begin by using the ratio test. You could do the ratio test on any one of the three because of Theorem 9.21. Again, Theorem 9.21 states that the radius of convergence of the series obtained by differentiating or integrating a power series is the same as that of the original power series. So maybe I'll do the ratio test on the original power series, but I don't need to do the ratio test on the other two because all three will have the same radius of convergence. I do need to check for convergence at the endpoints for all three power series. So I begin with this limit from the ratio test. So I take the limit as n approaches infinity of the absolute value of the quotient of the n plus 1th and the nth terms. And I want to find the values of x for which this limit will be less than 1. So you have the absolute value of the quotient of the n plus 1th and the nth terms. So how do you divide? You multiply by the reciprocal of the divisor. And of course, we can rewrite x to the n plus 1 like this, x to the n times x to the first, allowing us to cancel the common factor of x to the n. And that gives us the limit as n approaches infinity of the absolute value of x times n over n plus 1. And of course, we're taking the limit as n is approaching infinity. So you treat the absolute value of x as a constant, and you can factor it out of the limit. And when you do that, this is what you have. And of course, the limit here is equal to 1. So the limit from the ratio test for the power series f of x is the absolute value of x. So when will this power series converge? When this limit from the ratio test is less than 1, as you see from the ratio test. So you've got to make sure that you find the values of x for which the limit will be less than 1. This is an absolute value inequality. So this is what we call a compound inequality. But what we find here is that the radius of convergence is 1 unit. So all three power series will have the same radius of convergence. So if you're looking for the interval of convergence for each power series, now you basically just have to check for convergence or divergence at x is equal to -1 and x is equal to +1 for each of your three power series. Again, we're able to do that because of Theorem 9.21, which tells us that all three power series, the original as well as the derivative and the integral, will have the same radius of convergence, but they could have different intervals of convergence as a result of the behavior at the endpoints. So to complete the problem, we just need to check for convergence or divergence at x is equal to +1 and at x is equal to -1 for each of our three power series. So we will have to basically check for the right endpoint and the left endpoint for three power series. So we'll be doing 6 mini problems to conclude our lesson. However, we are saving time because we're using Theorem 9.21, so we no longer have to do the ratio test for the other two power series. So going back to our problem, we will begin by checking for the convergence or divergence of the power series here at the endpoints of this interval at x is equal to 1 and x is equal to -1. And then we'll check for the convergence or divergence of the power series for parts A and C, the integral and the derivative, at the endpoints of x is equal to +1 and x is equal to -1. And of course, these are the power series that we have for the integral of f of x and the derivative of f of x. So for the function f of x is equal to this power series, we've already determined that the radius of convergence is 1. So at the endpoints of that interval, we need to check for the convergence or divergence of the series, of the power series, using a different test than the ratio test, because the limit for the ratio test would be 1, and therefore the ratio test would be inconclusive. So what we need to do now is the following. Substitute 1 for x in the power series for f, and when we do that, this is what we get. So we get this harmonic series, which we know diverges. So that was pretty quick. Now if we substitute x is equal to -1, what do we get? So we're going to get f of x is equal to -1 to the n over n, which you can write this way. This is an alternating series, so now you can apply the alternating series test, check for the two conditions, the limit of a sub n as n goes to infinity, that is equal to 0, and check for a sub n plus 1, is that less than or equal to a sub n, for all n greater than or equal to 1, where n is an integer. Is that the case? Well, a sub n plus 1 would be 1 over n plus 1. And is that less than or equal to a sub n? A sub n is 1 over n, and the two fractions have the same numerator, so the one with the larger denominator will in fact be smaller. So the interval of convergence includes x is equal to -1, as this series converges by the alternating series test. But it does not include x is equal to +1, as this series diverges. So to conclude, the interval of convergence for this power series is x values from -1 to +1, including -1, but not including +1. And that's for f of x. Now we'd like to check for the convergence or divergence of the power series for the integral of f of x dx. Again, just at the endpoints, at x is equal to -1 and x is equal to +1. So here's the power series. This is the constant of integration. So we're just going to substitute x is equal to 1 and x is equal to -1 and check for each of those individually. So when we substitute 1 for x, this is what we have. You can of course simplify. The numerator is just going to be 1. 1 raised to any power is 1. And the denominator, you can see you have n times n plus 1, which you can write as n squared plus n. And how do you determine whether this series converges or diverges? You can do the limit comparison test, where our comparison series will be a p-series. So we will use a p-series as our comparison series from n is equal to 1 to infinity. And the highest degree that we have in the denominator of our series is second degree. So we're going to use a p-series with p equal to 2. And of course, we know that this particular p-series converges. A p-series converges if you have a p-value that's greater than 1. Converges by p-series test. And what we now do is use the limit comparison test. So this is step 1. Step 2 is to do the limit comparison test. You take the limit as n approaches infinity of the quotient of the nth terms of your two series. You can form the quotient in either way. I'll just have it formed this way. It doesn't really matter for some problems. Other problems, one way might be easier for you to evaluate the limit. So now you have the limit as n approaches infinity of n squared over n squared plus n. And because you have a rational function with the degree of the numerator and the degree of the denominator equal, the limit here is equal to the quotient of the leading coefficients, which is 1 over 1, which is of course 1. And because the limit here is a positive number, the limit comparison test tells us that our series that we're considering must converge because its comparison series converges. And I just wrote my conclusion on the right side of the screen in red. But what that tells us is that the interval of convergence will include the endpoint x is equal to 1. So now we still have to check to see if the interval of convergence will include x is equal to -1, and we'll check for that now. So when we substitute -1 for x in the power series for the integral of f of x dx, what we see is that we have an alternating series, so we may apply the alternating series test. So we may rewrite it as I've done here. I've also distributed the n to the n plus 1 to get 1 over n squared plus n. We have an alternating series, so we use the alternating series test. We check for the limit of a sub n as n goes to infinity. Is it 0? Yes, it is. And we check for this other condition, is the n plus 1th term less than or equal to the nth term for all n? And the answer is yes. If you look at the n plus 1th term, which is what we have here, and compare it to the nth term, the numerators are the same, so the fraction with the larger denominator will be smaller. So the interval of convergence will include x is equal to -1 because we just found, using the alternating series test, that the series that we have when x is equal to -1 does converge. So the interval of convergence includes both endpoints for the power series for the integral of f of x dx. The only work that we have to do now is to determine the convergence or divergence of the series, of the power series for f prime of x at the endpoints x is equal to 1 and x is equal to -1. So we begin by checking for convergence or divergence of the power series for f prime at x is equal to +1. We substitute 1 for x, and when we do that, this is what we have. This is just 1. For any n, we will just have 1. So if you take the limit of the nth term as n goes to infinity, you get the limit of a sub n as n goes to infinity. That would be equal to the limit of 1 as n goes to infinity, which is equal to 1, which is not 0. So this series diverges by the nth term test for divergence. And I wrote my conclusion there at the very bottom. So we know that the interval of convergence will not include x is equal to 1. But we still have a question about whether the interval of convergence will include x is equal to -1. So we'll check for that now. So when x is equal to -1, we just get a series whose terms alternate between +1 and -1. So there is no one particular value that the partial sums are approaching as n goes to infinity. The partial sums will always alternate. The partial sums will always alternate between 1 and 0, so the limit of the nth partial sum as n goes to infinity does not exist. And what does it mean for a series to converge? It means that its sequence of partial sums converges. But what we're seeing here is that its sequence of partial sums does not converge because the limit of the nth partial sum as n goes to infinity does not exist. So we can say confidently that the interval of convergence will not include -1. So the interval of convergence is from -1 to +1, not including the endpoints. Again, in the very last example, I referenced the definitions of convergent and divergent series. What does it mean for a series to converge? You look at its sequence of partial sums. If its sequence of partial sums converges, then the series converges. If its sequence of partial sums diverges, then the series diverges. And here, with the power series for f prime when x is equal to -1, its sequence of partial sums diverges, so the series diverges. Today we looked at these two objectives. Given a power series where the domain of f is the set of all x for which the power series converges, we were able to find the power series for f prime and the integral of f by differentiating the power series for f and integrating the power series for f. And then we were able to find the intervals of convergence for f, f prime, and the integral of f of x dx, the intervals of convergence for the power series for these functions. By using the ratio test and using Theorem 9.21, we only had to apply the ratio test one time, but we had to check for convergence or divergence at the endpoints of each interval for all three power series.